So my name is Joel Anderson. I am a student of Robert Harrison. My research focuses on numerical solution of the Dirac equation in madness, which is a code that our group works on. Many of you might be familiar with the Schrodinger equation, which kind of forms the backbone of quantum mechanics and quantum chemistry. The problem with that, or at least one approximation makes it doesn't account for the effects of special relativity. And effectively, electrons move fast enough that in some cases the contributions of special relativity make significant changes to the wave function and any properties that you might want to calculate. For lighter atoms, this is necessary for high accuracy calculations, or for heavier atoms, say the third row or below on the periodic table, these really aren't necessary for even qualitative calculations. And when you incorporate special relativity into the Schrodinger equation, you arrive at the Dirac equation, which is this top one here. You have your free particle Hamiltonian HD and the potential that the particle experiences. I've written out the Hamiltonian in its kind of full glory here. It's a 4x4 matrix, so where the Schrodinger equation is a single partial differential equation, the Dirac equation is actually a system of 4 PDEs. And the traditional approach of solving this is to project the equation into some basis set. You'll end up with a matrix algebra problem, and you use standard linear algebra routines to solve that. And you get an exact solution to your approximate equation. In madness, we do something a little differently, where we instead project our functions into this basis of piecewise polynomials, and we get adaptive refinement by splitting our domain as needed, but bisecting our domain as needed, and having scale basis functions in the smaller boxes. So I've written, in that basis, we can't do the normal matrix algebra routine. So we instead solve the integral equation, which I've written here, where I've now written this for multiple electrons. I indexes over the electrons and N indexes over the iteration number. And I have some preliminary results here in a table where I've calculated the ground state energy of some atoms and some small molecules. The comparison of this table is not quite as straightforward as saying, look how close they are, but it's a good first order approximation. So we're really excited with the agreement that we see here. And my poster is at the end of the hallway, so if you want to ask more questions, feel free to stop by.